Hello and welcome back. We are discussing section 1.5, limits. This video is the third and final video from the section discussing this last learning objective, investigate limits involving infinity. Everybody loves infinity, right? So let me get down to this relevant slide. Okay, so limits at infinity. Basically, what we want to incorporate into our limit lexicon is the ability to replace looking at a particular value that x is approaching with the notion of just letting x get really, really big or letting x get really, really small. And by really, really small, I mean big in the negative direction. So the way we'll formalize that is that either x is headed toward infinity or x is headed toward negative infinity. And this phrase, I fully acknowledge, is not perfectly accessible to everybody, but increases without bound is this notion of getting bigger and bigger and bigger and never stopping. So it doesn't have a ceiling anywhere, it just keeps getting bigger and bigger. So the way we want to write this is we'll say if x gets really, 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 really big, if f of x gets close to something, again, I'm using L to think about limits, then our notation looks like that. And everything here is identical to the way limits were defined in the prior two videos, except that instead of a concrete number, like x approaching 3 or -1, x is now, by this notation, approaching infinity. So as x gets really, really big. And this is just an effort to preserve the same notation that we're using, but still incorporate this goal. And one real-world way of thinking about why this might be a goal is if we think about the, quote, long run. So if time was our variable, then as t gets bigger and bigger and bigger and bigger, that is the long run as time goes on, what might happen to our total sales or profit for some function, for some company, or demand for some product, etc. So to pair with this, we also incorporate the possibility that x decreases without bound, so that x gets smaller and smaller in the negative direction. And I've picked a different label k here just so, although I don't know if there'd be any confusion, but another limiting value. And the only difference in notation is here, that we are going toward a negative infinity to account for the fact that we want x to get small, or rather large, in the negative direction. And then just to note that that whole wall of text that we had, properties of limits in green a few slides ago from the previous two videos, in fact, all of those things still apply. We basically get to break limits up over addition, subtraction, pieces that are being raised to some power, and so on. And just the note to cover the bases, it was always a requirement that each of those limits actually exist, and it's still the case here. That as we go to infinity, there needs to be some actual number that we get close to in order to apply all those properties of limits from before. So we had two helpful limits just approaching concrete numbers, and now we've got two helpful limits for approaching infinity or negative infinity. So if k has to be a positive value, and in fact it's an exponent in each of these cases, we could just say we need a positive exponent. But if we take 1 over x to some positive number, then as we go really far to the right on this graph, as x gets bigger and bigger, we're going to get closer and closer to 0. And the same thing is true. So notice it's the same 1 over x to the k in either case. But as x goes toward negative infinity, this function also approaches 0. I'm pretty visual, so I like to have a graphical perspective on this as well. You'll notice that there are a handful of versions of this graph. I guess probably basically the nicest versions of these. So these are with k equals 1, so x to the first, k equals 2, and k equals 3. And each of these graphs is an indication of this function's behavior, but for this purpose, what we're really looking at is as we go to the right. So if we follow these graphs really, really far out, what we should observe is that they're getting closer and closer to this horizontal axis, because that's what it means for the output of this function to get close to 0 as x gets really big. That means as x approaches infinity, these outputs are supposed to be approaching 0. And if you notice, they kind of do it in a different way on the left side. Some of them approach from the bottom, some of them approach from the top. But they're really accomplishing the same goal. No matter where you're coming from, it is approaching this horizontal axis. So as x approaches negative infinity for functions of this type, we're getting an output that's closer and closer to a value of 0. So just like we used x approaches a, implying that x approaches a, and as x approaches a, the limit of some constant is just that constant, the two helpful limits we had earlier, we're going to make a lot of use of these whenever we see x approaching infinity in some limit. Okay, so this might look familiar if you watched the first video for this section. So revisiting this example where we're producing heavy water used for nuclear reactors, we're going to have a cost function of 3x plus 130, that's in thousands of dollars. And instead of asking, if you recall what we did before, approaching some finite value of production levels, I think it was 10 gallons that we were looking for. What happens as our production level grows without bound? And again, I'm trying to help develop these skills, but as production level, so how much we produce is x. It's not c. So this is saying as x approaches, grows without bound, it means approaches infinity. It's getting bigger and bigger and never stopping. So this is just translating those words into something mathematical. So what is the value of average cost approach? So we have to be careful again. It's not just this function back again. We have to do a little bit of extra modification to get average cost function. But we know once we do that, we're going to be asking for x to go to infinity. Okay, so the limit that we're looking for, limit as x goes to infinity, and then here's average cost. We're sort of shortcutting it because we did this again in an earlier example, but on top here is the cost function, back again, just total cost, 3x plus 130, and then average cost is defined to be that divided by our production level, so divided by x in this case. Now, we can either simplify this first or use one of our strategies to evaluate this limit at infinity. And this is the great thing. We can't really plug in infinity, but we can look at behavior of these functions using our two handy limits at infinity to try to evaluate. So here's a strategy that can be kind of useful to us. Basically, the strategy says, cut down the exponents in top and bottom of this fraction by as much as is necessary to get rid of the stuff in the bottom. That's a lot of words for this, but the slightly more mathy version of it is divide numerator denominator by the term that has the largest exponent in the bottom. Okay, so here's what that kind of looks like, and if you're thinking about a shortcut, then that's great. We'll address that in just a minute. So limit as x goes to infinity of, here's average cost. It is a fraction, so if you notice x in the bottom, that's the largest exponent we've got. So the strategy says divide everybody by the largest term you can find. So there's x. Largest term in the denominator is the only term in the denominator in this case. So with a little tidying, x over x is 1. And then we do have to make sure that each of these things gets divided by x. 3x over x is 3 again, and 130 over x. That ought to look familiar, but can be reduced to just 3 plus 130 over x. And then we've got our nice properties of limits that say, all right, you basically get to ignore this 3. Just say, okay, it's going to be the limit of 3, which is not affected by x's at all. That's still just going to be 3 when you come out of this. So let's leave that out of the limit. You've got 100, this maybe takes a little a moment to recognize the algebra behind it, but you take this 130, and that piece is essentially the same thing as saying 130 times 1 over x, because the 130 would get dumped into the numerator anyway. So really we have the only thing with x's in it is the limit as x goes to infinity of this expression. The rest of all the little numerical stuff pulled out. Well, here's where we make use of that helpful limit to infinity that we had from before. This is limit as x goes to infinity of 1 over x to the first. X to the first, that 1 is certainly a positive exponent, so those nice helpful limits from that previous slide all apply. It means that as x gets big, 1 over x is going to get very tiny. And hopefully we can justify this in our heads too. If we take 1 over a billion, 1 over a trillion, 1 over 10 to the 150th, we're getting a number that has 0.000000000, etc. Has lots of zeros in it and is getting closer and closer to 0. So then that limit is actually equal to 0. This is maybe the first moment where you might notice it's not about what we can plug in, because I can't actually plug in infinity here. But I can say that as we get closer and closer to infinity, this fraction is approaching 0. And that limit is only interested in that trend. That's all it cares about. It is pointing towards 0, so that's what the limit is equal to. And then we've got 130 times 0. That all goes away, and our answer is just 3. So here's an interesting perspective on this. Here was our cost function, our total cost function. And this 130 was some overhead, fixed costs associated with making this heavy water. And we remarked originally that the 3 piece of this was really how much it cost per gallon to produce this heavy water, about $3,000 per gallon. Well, that's actually what our limit says. If we increase our production level and keep increasing it, we want to produce, we can't actually produce infinitely much heavy water, but if we wanted to produce as much as humanly possible, basically what's getting lost in the mix is this overhead cost gets completely overwhelmed by the actual unit cost, the variable cost associated with producing this, as long as what we're producing is just a really awful lot of heavy water. So what this says is in the long run, as production level increases toward infinity, we produce more and more heavy water. What we're really seeing in average cost is just the average cost of producing the water, not the fixed costs. But again, this is a limit. We never actually reach infinity. This is just what it's pointing toward. Average cost would always be something just a little bit above 3, even when we're producing a great deal. And then just a note, we could have produced this, this expression a little bit easier. We could have just taken this original fraction and divided x into each of them. I wanted to illustrate this process though because there are more complicated expressions where it really is useful to do this division, to take the top and bottom and divide by that largest term you see in the denominator. So I wanted to illustrate the process, but acknowledge those of you who noticed that alternative path. So at any rate, here's our final conclusion, even though I got excited and took a little detour. So as the volume of water increases, we want to produce more and more heavy water, and the average cost is going to approach $3,000 per gallon. Well, that does it for section 1.5, so concludes video number 3. I'll see you for section 1.6.